Yes.
Okay. Hi, everyone. My name is Jonathan Alcala, and along with Kennedy, we'll be presenting our project titled Applying a Multiple Layer Perceptron, or MLP. Here's a quick overview of what we'll cover. We'll start with the project overview, then go through data preparation, model development, and evaluation and tuning. Finally, we'll wrap up with the results and takeaways, as well as a reflection covering key topics. So the objective of our project was to predict income categories, either greater than 50K or less than 50K, based on demographic variables. The UCI adult income dataset includes both categorical and numerical data such as age, education, occupation, and weekly hours worked. Well, we use PyTorch to build our MLP, allowing us to handle tensor-based training and optimization. Our focus was to design an efficient model pipeline from pre-processing through evaluation, while controlling for overfitting and class imbalance. So we began with the flat CSV file of the adult income data set and went through five key pre-processing stages. First, we cleaned the data, trimming strings, replacing question mark values with unknown, and dropping redundant columns like education, since education number carries the information numerically. Then we one hot encoded all categorical variables, which expanded our feature space to 91 columns. Next, we standardize the numeric columns, so all features are on comparable scales, which helps the MLP converge faster. After that, we split the data 80/20 into training and validation sets to evaluate generalization. Finally, we converted everything into PyTorch tensors and wrapped them in a data loader with a batch size of 64 for efficient mini batch training. Our MLP architecture started with 91 input features. We used two hidden layers, 128 and 64 neurons, each followed by a ReLU activation and a dropout layer of zero point 0.3 to prevent overfitting. The output layer had two neurons for binary classification, producing raw logits. ReLU introduced nonlinearity and speeds up convergence by zeroing out negative values. We trained with cross entropy loss for classification and the atom optimizer with the learning rate of 0.001 over 20 epochs. After training for 20 epochs, our model achieved about an 85% validation accuracy. The training loss decreased steadily, while validation loss started increasing slightly after 8 to 10 epochs. A mild sign of overfitting. Here we see the confusion matrix. The model performs well on the majority class, which is less than or equal to 50K, but misses some of the higher income cases, which explains the recall drop. This plot shows how the model learns. Validation loss stabilizes while training loss keeps improving. A classic indicator that we might want to implement early stopping. Next, we performed hyperparameter tuning across five candidates, A through E. We varied four main parameters: hidden layer size, dropout rates, learning rates, activation functions such as ReLU, leaky ReLU, and TON. All models achieved strong validation accuracy between 84% and 85%, showing that our pre-processed pipeline is stable. The best candidate, B, with layers of 256 and 128 neurons, relay activation and the dropout of zero point 0.3 and the learning rate of 0.001 showed the most consistent and lowest validation loss. These curves demonstrate that all candidates converge smoothly, meaning the model and optimizer were configured effectively. We then refined our top candidate B to see if small changes could improve results. First, we tried a low dropout model with 0.25. It slightly increased recall but reduced overall accuracy, suggesting mild overfitting. Next, we tested a class-weighted model that addresses the 3-to-1 imbalance. This boosted recall to 79%, but lowered precision and overall accuracy to 82%. In the end, we kept candidate B with dropout of 0.3 and no class weights because it offered the best balance between accuracy, around 85%, and precision, which was 75%. So This configuration generalizes well, was interpretable, and performs consistently across both income classes. Finally, we use a training model to generate predictions on unseen validation inputs and exported them to a CSV for evaluation. So the main takeaway is that our MLP delivered a strong baseline for tabular data with mild overfitting but solid stability. Future work could include early stopping, oversampling, or benchmarking against tree-based models like XGBoost for comparison.
Yeah, and when it came to the reflection questions, the first one was asking sort of why we picked the model architectures that we chose. And to summarize this slide, it's because it's what turned out best with candidate B when compared to the other candidates. But the number of neurons, it allowed the model to understand the broader patterns in the data while remaining sensitive to local patterns. For the activation function, it added nonlinearity and it performed the best when compared to a leaky ReLU or the TAN-H activation function. For the dropout level, as you heard, 30% of the neurons in that layer will be randomly set to 0 during each training step to prevent overfitting. The typical range is 0.20 to 0.50. And our 0.25 dropout level didn't perform the best, so we upped it a little bit. No need to go crazy and do 50%, but keeping it toward that lower standard end worked well for us. And then the binary output layer, not only was it what was described in the project, but it does work well with the cross entropy loss, and I don't think it overcomplicates the scenario. If we were trying to, classify every $10,000 and group people into different incomes based off of that, I think the model would have gotten a lot more complex and definitely had a loss in accuracy. But I think keeping it to above 50K and below 50K really made the scenario less complex and uh, allowed the model to learn the data better. So for overfitting, the way that we monitored and mitigated the overfitting was really through those dropout layers. I found this helpful graphic for a neural network dropout sort of before and after. And as you can see on the left, every node is active. It passes through everything. But on the right-hand side, you'll see that the neural network after dropout has some squares that are now, or circles that are now red. And those are the nodes that get essentially skipped. So instead of going through each and every possible node, it's going to sort of skip some on each layer to hopefully stop the model from memorizing the data, which is really what leads to that overfitting. It becomes a little too sensitive to changes in the data and wouldn't perform as well on new data. But when we do this dropout, we're encouraging the model to not learn the patterns of the data at hand, but really get good at predicting. Some honorable mentions was using ReLU activation function, using a controlled training duration of 20 epochs, and then using the atom optimizer. For ethical concerns, there's four primary ethical concerns we have here. Historical bias in the data set. Adult income data can really reflect the past inequalities in occupation, income, gender, and race. Risk of discrimination in predictions. The MLP may learn those patterns that disadvantage certain demographic groups and replicate them. Proxy variables for sensitive attributes, even if we were to go in and remove race or gender or mask them in some way, the MLP is usually able to infer them through other related features, job type, marital status, education level, some of those key features in there. And then limited model explainability. What is most concerning is that the MLP is not easily interpretable. So it's sort of difficult to justify or audit the decisions it makes. You'd have to sort of retrace your steps through every node, through every layer, and it would be harder to know what to change in order to make this model more equitable. But really, what this boils down to is that this could lead to real world harm if this were to be used to figure out who should have loans at a bank, if this were to be used during hiring, if this were to be used when deciding who to give a house to over various applicants. If it learned this bias and it learned sort of this discrimination and then unfairly rejected people from jobs, loans, home applications, things like that, that would be really harmful. And just in general, it reinforces stereotypes and the systemic disadvantages. And then, last but not least, there are privacy concerns. No one technically consented to having this MLP done by Jonathan and I done on them. And this is a very popular data set when it comes to machine learning. So while there's nothing very personally identifiable, we do always have to sort of battle with that concern of, do people consent to this information being out there and used in different models, public or private? And then the last one was about activation functions, sort of why activation functions are necessary in neural networks. And activation functions are how we introduce nonlinearity and capture those complex relationships in a model. In the real world, data is very messy and it is usually not perfectly linear. That's why ReLU, the sigmoid function, hyperbolic tangent, which we saw here, and many, many more activation functions are incredibly essential. They make the neural networks more feasible for real world data. For this project, without those nonlinear activation functions, the network would simply be a linear model and the model wouldn't be able to learn the complex patterns in the data. And then this is a bit of a flashback from slide 5, but it is our ReLU activation function that we ended up using in this model.
And that concludes our presentation. Thank you for listening. Okay. And you can